All right, let's look at the worksheet for Chapter 6, Section 4, starting with some multiple choice. Number 1, in metals, the valence electrons are considered to be, so again, we're not talking about kernel electrons here, we're not talking about inner shell electrons, we're talking about the valence electrons, and we're talking about metals. We're talking about metals, so let's get this straight. Are they attached to particular positive ions? Not if you remember what the sea of electrons model suggests. Okay, they are not. They're actually ejected because they're metals on the left side of the periodic table. They want to satisfy the octet rule, and their best strategy for doing that is to lose electrons. So they're donating electrons. These electrons are just going into this kind of a wishing well situation, and they're not attracted to any particular positive ion. They're attracted to all of them at the same time. Okay, so not that one. Are they immobile? No, that's actually why we have the sea of electrons model, because these electrons are highly mobile. Okay, they're delocalized. They are not attached to one locale. Involved in covalent bonds? Well, we're talking about metals, and when we talk about covalent bonds, we're talking about non-metals bonding together. So no on that one. Shared by all surrounding they're shared by all of these metals at the same time, and there's a multi-directional attraction to each and every one of these electrons. So we're going to go with a B. Number 2, the fact that metals are malleable and ionic crystals are brittle is best explained in terms of their polarity. Well, no. Okay. One side of a particular formula unit or structure being partially positive and the other being partially negative doesn't apply to metals, okay? And it doesn't apply to ionic crystals, because the formula units that form these crystals are going to overall balance themselves out, so there's not going to be a partial positive, partial negative end of the entire structure. Enthalpies of vaporization, well, we haven't talked about that ever, so let's go ahead and say no. London dispersion forces, that's something for another section. Again, we haven't talked about that yet. By process of elimination, I'm going to conclude that's chemical bonds. Okay, and that is true. When you look at metals, the reason that they are malleable is because of the sea of electrons. Its ability, the delocalized electrons, giving it the ability to move, have those positive ions move, therefore the structure moving, okay, being bent, and not ever experiencing some sort of positive repulsion and breaking, is due to the way they bond, right? The sea of electrons model. However, ionic crystals, because if you remember the PowerPoint notes, when you apply force to one of these crystals, you can change which ions are lined up with which, so that you can have like charges next to each other and start to feel that repulsion, and then you can have that crystal shatter. So that has to do with the way those things bond chemically. Number 3, as light strikes the surface of a metal, the electrons in the electron C. Okay, so we're talking about a metal, so we're talking about the electron C. Let's see, allow light to pass through. Well, no. When light comes into contact with anything, we learn from Chapter 4 that those photons are either going to bounce off, they're going to collide and bounce off, not be absorbed, or they are going to be absorbed and they're going to excite those electrons to a higher energy level. B, become attached to particular positive ions. Well, we're in a metal, okay, so we're talking about the electron C, so no, we're not going to be attached to positive ions. That defeats the purpose of the electron C. Fall to lower energy levels? No. When light strikes, when a photon strikes an atom, that photon is either going to be absorbed or it's going to be deflected. Okay, there's no way that that's going to involve a lowering of energy level. The only thing it could possibly do is raise the energy level, if anything at all. And so we are left absorb and re-emit that light. So when that light strikes it, it can be absorbed. Okay, and then after a time, that electron will drop in energy and then re-emit that photon that it just absorbed, re-emitting the light. So we're going to go with D for number 3. Number 4, mobile electrons in the metallic bond are responsible for A, luster. That's true. Okay, so luster, again, shining. This is very closely related to number 3. As light strikes the surface, it's absorbed and re-emitted. Okay, well, that's luster. That's shining. Okay, that's the shining essence that you see on metals. So that's a good one. But here's the thing. I just read A, and I said, I like A. I think A is correct. I haven't read any of the other responses yet. And remember, there were a number of us who made silly mistakes on the last quiz that cost us what could have been a pretty high score with how well we were doing with the content. So let's make sure we read the other options. Thermal conductivity. Wait a minute. Metals conduct heat very, very efficiently. They also conduct electricity. So if there's an option here that refers to conductivity of electricity, there is. It's all of these. And look at this. D, all of the above. Okay, all of the above. 5, in general, the strength of the metallic bond blank moving left to right on any row in the periodic table. So the strength of the metallic bond, how strong each of those metal cations are being held in place, changes in what direction? Okay, does it increase? Does it decrease? Does it remain the same? Or does it vary in some other way that we can't really represent well with a trend like that? Okay, as we go from left to right across a row, okay, horizontally. Now, one model I do want to get across here, as you go from left to right in the periodic table, you are increasing in the number of protons. Yes, you are. You're also increasing in the number of valence electrons that neutral atom has. For example, as you go from lithium having 3 protons and 1 valence electron, you go to beryllium, 4 protons and 2 valence electrons. And then you go to boron, you have 3 valence electrons. And so realize, in order to satisfy the octet rule and gain a noble gas electron configuration, each of those elements that I just named are going to donate 1 more electron than each of its predecessors, right? So lithium is going to donate 1 electron. Beryllium is going to donate 2 valence electrons. And then boron is going to donate 3. And so each of those elements, okay, are going to have various charges. Move this over here. So I'll go... Lithium is going to be +1, beryllium is going to be +2, and then boron is going to be +3. Well, remember that electrostatic forces are based in the opposite charges attract, unlike charges attract. That's where we're coming from. So as we go from left to right in the periodic table, we're seeing that the magnitude of the positive charge is increasing. And so if we're increasing the magnitude of the positive charge, there's going to be more attraction on any negatively charged particle, regardless of whether it's a small amount of negative charge or a large amount of negative charge. It doesn't matter. What's really changing here, or at the very least what's changing, is the magnitude of positive charge. So as we go across from left to right in the periodic table, we're seeing this magnitude increase. Therefore, we're going to see the strength of the metallic bond increase. I'm going to go with A. Last multiple choice question. When a metal is drawn into a wire, okay, the metallic bonds break easily? No, they don't. Metals are drawn into wires pretty easily. That's the trait of called ductility. They break with difficulty. Well, when you're drawing metals into wires, the idea is that they don't break. So breaking with difficulty, not really what we're going for here. Do not break. Well, I just said that, so that's a good one because we're drawing them into wires, right? When a metal is drawn into a wire successfully here, notice that the question is saying it is being drawn into a wire. Those bonds aren't breaking. But just for completeness sake, let's look at D. Become ionic bonds. No, they're all metals. Okay, they're all metals. In order to have an ionic bond, you have to have a positive, okay, metal, okay, that'd be a positive, but you have to have a negative. There are no nonmetals here. We're talking about a sample of metal, so it's all positive. So no on the ionic bond. I'm going to go with C, do not break.